And we're good to go. How's that? Actually, I'll get started for the coffee. So we're on page what, please?
1024?
Wow, 1024. That's a lot of pages.
I agree. It's a good thing we're only doing a third of it at a time.
Yeah. Okay, and
Anything 13 through 16?
double intervals. 13 through 16. Hmm. Well, they don't even want you to calculate it, it's not necessary.
Well, sorry, finding the limits of those. Like that's, I feel like I'm pretty good at the whole integral thing and then double integration. It's setting up the limits that I struggle with.
Okay. First, this is the volume that we want, true? This is the volume we want. So at any point in this volume, we have a height z, true? And at any height, the z is given to 9 minus r squared to the 1/2 power, true? So I have no trouble with that. So this volume is going to be the integral of 9 minus r squared r d theta. Now, theta is going to go 0 to 2 pi. True? So we don't have any trouble with that. And r is going to vary between 1 and 3. So these are your limits. But it's backwards, 1 and 3 is the inside. The r comes first. So 1, 3, 0, 2 pi.
Well, I guess number 14.
Well, let me check now. Z, this is only going to give us the hemisphere now. It's only going to give us half the answer. Because Z is actually equal to plus or minus this, agreed? So we have to do it a half at a time.
Okay.
So you agree that the volume is ZdA?
Yes.
Okay. And you agree that dA in polar coordinates is r d theta, dr d theta.
Yes.
And Z is the vertical height inside the sphere. And the equation for the sphere is x squared plus y squared plus z squared equals 9. And this is r squared plus z squared equals 9 in polar coordinates. So z is equal to plus or minus 9 minus r squared to 1/2.
How come you set it up as z equals r versus r equals z?
Because a method of solving it is to integrate across the footprint. And the footprint is in the z0 plane. It's in the r theta. I'm going to integrate with r and theta. I need to remove z. I need to express z in terms of r and theta because I'm integrating r and I'm integrating theta.
Okay.
Now, there's another way to do this where you leave z in. That's a different approach. This is the approach where you take z out. And when they said they wanted to express as two coordinates, then we take z out. There's only leave r and theta. There are 3 or 4 different ways you can do this, and this is the way they asked for at this time, r d theta. Okay? And the other way that you can do it is instead of substituting out z, you can just have a triple integral, dz, r d theta, r d theta, and then you integrate z between those limits. But it comes to the same thing, and we do triple integrals later tonight. But since you only have double integrals now, you have to take out one of the parameters.
Okay.
Now, you can just do this in your head. Okay? You don't need this, just geometrically. What's the volume of that sphere? 4/3 pi r cubed, agreed? R is 3. Now, there's a cylinder in the middle. The volume of the cylinder is pi r squared h.
Okay.
So you subtract the cylinder from the sphere, and you've got your geometric answer. You can do it by geometry. Yes, sir. Yeah. But what good is geometry when you can do integrals, huh?
Yeah.
Okay, so this is how you want to set it up. Your limits of integration. R goes from 1 to 3. And theta is all of 2 pi. You substitute out z by the equation for the sphere.
So then, like, what about number 14?
Okay, the green cone has a polar coordinates z equals r, agreed?
Yes.
So that substitutes out, it's just, so your integral of z, so 14, your volume is the integral of z r d theta, r d theta, agreed? Now, in this z equals r,
Okay.
so it's the integral of r dot r dot dr d theta. So now just what are your limits of integration? And et cetera, et cetera. Now,
So like the part where it's inside x squared plus y squared equals 2y.
that's the x squared plus r squared equals 2y. Well, z equals r is the boundary. That's the upper limit.
Okay.
Okay, so that's a slice. And inside of x squared plus y squared equals 2y.
I think one of the things that confused me the most is when they went from 2 dimensions to 3 dimensions.
Mm-hmm. It would. Hi, Monica.
Hi.
X squared plus y squared equals 2y. There's no z in that, it's a cylinder. Oh, I see how that's done. You have to complete the square on that. That's a circle, okay? And the circle is, but you can,
I swapped out x squared plus y squared for r squared,
yeah,
and then r sine theta for...
yes, right, I follow that.
So r equals square root of 2 sine theta.
Yes, that's right. Okay, so you can make that substitution too. But those are where your limits are going to go. But I want a picture of the footprint. And I think I just want to do it half at a time again. So let's draw the footprint on this. Well, I'm going to draw y in here, x in here, so it looks like the drawing, right? Yeah. And so theta goes with the positive x-axis, so I have to draw it the other way because of the definition of theta. So this is x, this is y, and this is the circle out here, agreed?
Yes.
So theta goes from 0 to pi.
Yes.
So theta goes from 0 to pi. So theta goes from 0 to pi. Okay? And what in the world is and r goes r goes from 0. Well, I think we have to break it into two pieces. Let's just do this piece right here. So let's just go out to pi over 2 and double it, okay? Otherwise, r goes from 0 to 0, full circle. So r here has, at this point, r has a value of 0. And at this point, r has a value of what?
Square root of 2.
Square root of 2. So r equals 0, square root of 2, and go to pi over 2 and double it.
Alright, so what I'm trying to do is get rid of the z's from this equation altogether and put r or theta
That's
into...
what you're trying to do. That's exactly what you're trying to do.
And then I'm trying to put it into r or theta, and then
Go to the footprint.
go to the footprint, and then I would integrate for r because r will vary as theta varies, and then I substitute in the value of theta out second.
Yes, that's right. And again, I got my limits typically backwards. R goes from 0 to square root of 2, and theta goes from 0 to pi over 2. And you double. Okay? Inside, outside. I buy my coffee at the right time. This is a hard section. Yes. Here, let me square it off even more, make it. Okay? Good. Okay, thank you very much. Very legible.
I forgot mine. My husband's bringing it right now.
A big improvement then.
Should be darker. I wrote it on the hard surface this time.
Okay, that helps a lot, yes. Yes, I can read this stuff. Yeah. Okay, it's in my box where it should be. Okay, good, thanks, guys. Questions, comments, remarks? What we've been doing in the few moments before class is a couple of examples on section 14.3, page 1024. And as everyone has discovered, these are hard problems. And so I think we should do a few jointly together. So Stuart asked for 14. So the general approach for doing these volume problems is a footprint and a canopy. If you have some canopy upstairs, which is the top of your volume, so it looks like that, and then you drop it down into the XY plane, and it's going to create a footprint in the XY plane. And you then want to calculate the volume that is under the canopy and above the footprint in the XY plane. So you break the XY plane into little small areas, dA, and you take those dAs and you extend them up to the canopy, so you make a little parallel pipette, and that parallel pipette has a volume, dV, which is equal to base times height. Well, the height is Z, and the base is dA. So Z is a function of X and Y. In other words, the height of the canopy is given. Z is some function of X and Y. That's given. So this approach works when Z is known to be a function of X and Y. Then you adopt this approach. And the regions of integration are across the footprint. So Z is not included in the integration. Only X and Y are in the integration. And the reason that it's actually a volume is because you have substituted out Z in terms of X and Y, but even after substitution, it's still there, and it's multiplying the little square on the bottom, giving you 3 dimensions, giving you height times weight. So the volume is the integral of dV, which means it's the double integral over X and Y of the height of the little parallel pipette times its base. Now this doesn't change if you go to polar coordinates. Then its polar coordinates, it still has a height Z. So it's still the integral of Z, only now dA is RD theta. For arguments that we've expressed last time. So Z is either a function of X and Y, or if it is a function of X and Y, you can substitute it to be a function of R and theta. By the substitutions, X equals R cosine of theta, and Y equals R sine of theta. So this is your general approach for both of these sections. And then we got into slightly harder problems when we allowed for the footprint not to be just a rectangle, a box, but for the footprint itself to have curved lines. But we didn't get so advanced to have all four sides curved. We only had pairs of opposite sides curved. The other two had to be held vertical. Then we learned how to play intellectual games, such as examining the footprint very closely. And the easiest way to examine the footprint very closely is to take its XY footprint and to just plot it out in terms of X and Y, and then examine very carefully what the limits of integration are in the XY plane, because that's where the footprint is. And if there are some slanted lines there or curved lines there, then you just write the equations down. And then we learned how to invert the order of integration, basically by inverting those equations. So this all sounds very simple, but when you try to do it, it's really hard to keep track of and to visualize and to do. So these are hard problems. So I don't have any examples selected, but perhaps you do. Do you have an example selected from these?
Number 15.
Number 15. He's on page 1024 again, and he's in polar coordinates. So, most of these are a matter of drawing the footprint. So, without these colors, if you're dealing with a Xerox copy, then you might have trouble with these colors. They help a lot. So this is section 14.2, page 1024, number 15. So the picture that we have here is that we have a hemisphere. Indeed, we have a hemisphere. Okay. Oh, that goes all the way back here, too. So we have a hemisphere, and the hemisphere is intersected by a cone, by a cylinder. So this intersection of a hemisphere and a cylinder is centered on the x-axis. So we have a cylinder here that's centered on the x-axis. So there's some intersection between the cylinder and the cone and the hemisphere, and that intersection gives the canopy, it gives the roof of this. So if we look at this from the side view, a straight side view, if this is the x-axis and this is the z-axis going up, then the straight side view would be that this goes from here to here, and it's a curved line though, because it's on a quadrant. Okay. But what you really need to do is to do the footprint. So the footprint is the base of the cylinder. Is everyone convinced that the footprint is the base of the cylinder? Does everyone see the cylinder in this drawing? Glenn, you see the cylinder? Hmm?
Yes.
You see the cylinder? Okay, so let's draw the cylinder in XY space, X and Y. So the cylinder goes out the X-axis, and you know that that is a circle. You get to complete the square. X squared plus y squared minus x equals 0 just means a displaced circle. And if you complete the square, then you find the center of the circle. And so x squared plus y squared minus x equals 0 is x squared minus x pi plus 1/4 plus y squared equals 1/4, and this is x minus 1/2 squared plus y squared equals 1/4. So where is the center of this circle?
1/2.
The center of the circle is at 1/2. and the radius of the circle is also 1/2. Okay? Now, if you want, we can do this in xy space, but there's no need. And now the upper limit of this, as we go from the floor up to the height here, is given by the intersection of the cylinder with the hemisphere. So the upper limit of it obeys the equation of the hemisphere, which is x squared, which is z. Oh wait, that's not a hemisphere. That's a paraboloid. That's not a hemisphere. So I shouldn't have drawn it that. It's a paraboloid. Z equals 1 minus x squared minus y squared. Okay. So that's the equation of the roof, the canopy. So it's a parabola of revolution. It's a parabola revolution. Okay. All right. So now that we've done the geometry and we have a feel for what's going on, the idea is to actually do the integral. So we've been requested to do the integral in polar coordinates. So the volume is the integral of z dA, which is the integral of z of r theta, r dr d theta. And I just do a one integral sign by habit, and then when I get around to putting the limits in, I actually put in 3. So now we have to convert z of x and y to z of r theta. Z equals 1 minus x squared plus y squared. Z equals 1 minus r squared. How did I do in that conversion? Did I convert z into polar coordinates? Okay. Good. So volume is going to be the double integral of 1 minus r squared, r dr d theta. And now let's go back to our footprint to get the limits of r and theta. So theta is the angle with the x-axis. So the original angle of r is here, and then it goes all the way around to being there again. So that's problematical because theta goes from 0 to 2 pi, if you will, and r has a beginning value of, this is out here at 1, isn't it? True? And then it goes to 0 and r goes back to 1 again. So the easiest thing to do when you have this kind of a situation is just to evaluate half of it and to multiply that result by 2, because then your limits are unambiguous and not problematical. So what we're going to do is just solve the volume of the upper half, and then we'll double that, because that way our limits are not problematical. In fact, our limits go from theta equals 0 to theta equals what? Here we have theta equals what? What's the angle that I have here now?
0.
And what's the angle I have here?
Pi over 2.
So are we all in favor? Theta goes 0 to pi over 2? Okay. From the beginning point to the end point of theta is 0 to pi over 2. Now r goes from 1, and r goes to intermediate values as well, agreed? But the final value of r is what? What's the value of r at that point? Is 0. So r goes from 1 to 0, and theta goes from 0 to pi over 2, and we just double the result, and we have unambiguous limits to our integration. So you can crank it out if you want to.
So the book has, for r, it goes from 0 to pi over 2, or 0 to cosine theta.
Oh, I see what they're doing. Yeah, and I probably stand corrected on that, because we have to give the limit of r in terms of theta, because it's not a box. So I'm just wrong on that. I was just much too simplistic. So, absolutely right. So let's go back to any one of our arbitrary r's here. The r is definitely varying in length, and the equation of this circle is given that x squared plus y squared minus x equals 0. So let's take this equation into polar form. Okay? So this is the equation of the footprint, the equation of the circle. So let's go into polar form on it, and what do we obtain? X squared plus y squared is what in polar coordinates? Lynn, do you know? X squared plus y squared in polar coordinates?
No, I don't remember.
Okay, can you reconstruct it? This is a point out here, has coordinates x and y, r and theta, okay? Now, I'm going to put in its x coordinates in green. This is x and this is y, true? Now I'm going to put in its polar coordinates in red. This is r and this is theta. So now please tell me the relation between x, y, and r, Lynn.
X, Y, and R, is it?
How are those three related?
Sine of theta is
No.
whatever
Don't need theta, just r, x, and y.
A squared plus B squared, or X squared plus Y squared plus R squared.
Good. So let's go back to this problem. We want to convert this to polar coordinates. So this much is what?
R squared.
R squared. Now let's go back to this again. Now, give me relation between r, x, and theta. X equals
Let's see.
x equals what? Here you have a triangle.
R cosine.
R cosine theta, very good. Okay, so let's go back to this. Minus R cosine theta equals 0. So we can say R squared equals R cosine theta, or R equals cosine theta. Okay. And so this R is equivalent to cosine theta, and so the limits of integration, or as Stewart points out, the book is very correctly saying, is going to be given by r equals 1 as its starting value, and well, at cosine theta it's going to be 1, and at any other point it's going to go from 1. The starting point of r is 1, and as a function of theta, then it is cosine theta. So let's change those again. Top is going to be cosine theta. Okay, I stand corrected, so I made the problem too simple. Okay, good. Book 1. Okay, so the r has to be, the inside integral has to be expressed, the limit has to be expressed as a function of the outside integral. This is also true when we had x's and y's. So I just overlooked that. I probably overlooked that in my solutions to 13 and 14 as well. So they probably have to be re-examined too.
Okay.
Good. Okay, so any other examples I can partially present? Now, let me pick one or two. Now, let's go back to X and Y, because they don't have the added complication of having to convert.
Well, where's the fun in that?
Converting, or where's the fun in not converting?
Not converting.
It might not be fun at all, but we might have to learn to walk before we can run. So let's just go to,
I agree, we should skip that topic on the test.
Seconded. Motion passes.
you should, what, skip the easy ones? Okay.
No, skip the polar ones.
Well, what fun is that?
It already made me polar. I'm good.
I don't know what it would be for third opinion, but I call third.
I have questions on how to figure out my limits.
Yeah, that's
I tried and I couldn't figure out. I Googled all types of videos trying to figure out how to set my limits.
You try coming to class?
I didn't. I had a soccer game that day.
Okay, but we spent most of the last class hour in this because it is so hard. Because since it is so hard, there's no sense we don't review it again, how to set the limits, because that is the hard part. You set the limits through the footprint in the XY plane. So let's go back to 14-1, which is a simple double integral. This is our starting point. Now, on page 1001, we want to find the volume of this object pictured at the bottom. So its z value is a function of x and y. So we integrate little parallel pipets of height z that have, each little parallel pipette has a base dx dy. So the integral z dx dy over the footprint is going to give you the volume. Okay? Now this is easily done when you have a box for your footprint, just a rectangle. Then you have fixed limits like I tried to do in the board in a harder case. And then we go to the next section where the footprint, that is a box, and the whole thing is done by working with the footprint. Then on page 1009 can be of two types, type 1 and type 2, where type 1 can have curvature on the y ends of the box, and type 2 can have curvature on the x ends of the box, but not both together. So when you have this curvature, then you have to do the orders in a certain, the integration in a certain order. For example, if you have a box of type 1 that has curves here and curves here, then if the only way that you can take your strips is in this order right here. So then the height, then the y integrand dy is going to, this is y1 of x and y2 of x. And so the dy integral is going to go from y1 to y2. And you're going to integrate out dy, creating a vertical strip. Then you have to do the x integral, which is going to go from point A to B. And here you have z of x and y again. So in this case, you have to do the y integral first. Now, if you have the curvy lines going this way, in your xy plane, and these are straight lines, then the only strips that you can make are strips in this direction. So you have to do, this is x1, this is x2, or x1, x2. So you have to integrate the x, and this is a function of y, and this is a function of y as well, from x1 of y to x2 of y. And this gives you just a function of y. And then you integrate that from A to B, and you're out of there. So depending on whether you're type 1 or type 2, you have to do the inside integral as prescribed. So you go from wavy line to wavy line.
No, that's only if they're constants.
Well, that's the only type we're dealing here. This is a simple course. We only have two, we're not going to do it with all four wavy lines at once.
Well, no, what I'm saying is if your limits are constants, right? So if your limit is an A and a B, you can interchange them, is my understanding.
A and
Based
B?
on what, well, no, not A and B, like, if you're going up and down or sides, you know, vertically or horizontally, you can interchange your integrals. However, if you have variables within your limits, is where it has to go, one has to go before the other. I got that, I understand, I did my reading, I watched your videos, whatever. But I don't understand, I can't figure out how to set my limits. That's the problem.
Okay. Now, there's two problems here. We'll address them both. The first, you have to figure out how to set your limits for a given problem. Then, if you want to switch your order of integration, that's a different problem. So you asked for the first one, which is to set the limits.
Set
okay?
the limits.
Let's take a specific case. Do you have a specific?
Well, I mean, on the, I don't know if the examples do it, but where you have a limit of like an x, 2x minus y.
Well, we have plenty of them. 2x minus y?
Well, I don't know, I don't know.
Yeah, well, okay, we have plenty of them here. So let's take example 3. Okay. Example 3. So the z height is given as xy. That's the function, agreed?
Where?
Example 3 in the middle of page 1011.
Oh,
Okay? So we want the double integral of xy dA on page 1011. Okay?
okay,
Now, xy represents the height of the parallel pipette, agreed? That's z.
correct, yes.
Okay, so that's what that is. Now we have to put in dA, which is going to be dx dy. Now the footprint is given in the drawing on the left side. Now this is a case that x is fixed between 2 and 4. And y varies from an upper y, which is the square root of x, a lower y, which is 1/2 x, okay? X over 2. So the picture is how you do it. So this is the picture. So this equation is y equals square root of x, and this is y equals 1/2 x, and we want to integrate in this region right here. So this is our footprint. Now, the curves are on the upper and lower, so what we have to do is integrate y from this region right here. So we have to integrate dy from its lower value, which is 1x over 2, to its upper value, which is the square root of x. So the picture is what tells you what the limits are.
How do you get x over 2?
Well, the
Am I-
equation of
I
this
don't know.
line is, what's the equation of this line?
1/2. And if you flip it, then it's 2.
So I didn't flip it, it's just 1/2 x equals x over 2.
Oh, okay.
You want to take?
Okay.
Okay, so now that we've integrated dy, what we have is the area of this little strip. But what's the area of this little strip is dx, agreed? The width of that little strip is dx. So the area of that little strip is its height times its width, which is square root of x minus x over 2 times dx. So that's the area of this strip. So that would be our second integral, is to take dx from the left side to the right side, which is 2 to 4. So after we do that, then the y is gone, agreed? So let's put in the actual functions now. So what we're going to do, so the volume is going to be the integral of xy dy dx. We're going to do the y integral first. It does not matter, from x over 2, the square root of x, from 2 to 4. Okay, so now in the first integration, x is a constant, so volume equals the integral 2 to 4, dx comes out, and it's the integral of y dy. Dx is just sitting here waiting. So we do the integral, inside integral first, and the limits of the inside integral are x over 2 to the square root of x. So The outside integrals stay the same. Integral 2 to 4, the x is sitting here waiting. And now this is going to be y squared over 2, evaluated between x over 2 and the square root of x. And then once that's done, it's going to be multiplied by dx. So it's going to be from 2 to 4, x. Now the square root of x squared is x over 2. And then when we square it, it's going to be x squared over 4 times 2 minus x squared over 8, d8. Okay, did I do that reasonably well? So this is equal to the integral from 2 to 4 of x squared over 2 minus x cubed over 8 dx. And then we're back to calculus 1. So you push it out. So the whole thing that's new here is the careful evaluation of the footprint. The careful evaluation of the footprint will lead you to set up your limits correctly. It will also lead you to interchange your limits correctly. So this is example 3.
Okay, so number 10,
On page?
on 1015, where you're identifying your limits of f of f, x of x and y.
Yes, okay. Now
There-
this is exactly the same. Now, you tell me now, because you're in good shape to do these answers now. Okay, go.
Well, there's no true x value, right? Am I supposed to solve
Solve. You're
for
supposed to
y
solve.
and flip
Supposed
them?
to solve. You're absolutely supposed to solve. No, you're supposed to see where those equations cross. That's the missing point. Yeah, there is a missing point there. You have this equation and this equation. Now, the top equation, so you need to know these coordinates, true?
Yeah,
Well, those are the intersection of the two curves. So the curves are square root of x and x squared. So those occur when the square root of x equals x squared. Because the point's on both curves, isn't it? The x
Yeah.
value of this obeys that equation, the x value of this obeys this equation. Okay? So you square both sides, x equals x fourth. So x fourth minus x equals 0. So x times x cubed minus 1 equals 0. So x equals 0, that's this point. And the other point is x equals 1. That's this point. You solve the two equations, true? So you found that point x equals 1. So now, what's the y value? The y value is also 1, isn't it? Because these two equations are y equals and y equals. So when x equals 1, y equals 1. So you find the endpoints because it's where the curves intersect. Simultaneous solution. That was the missing piece, right? Good question for that reason. Okay, so we're entertaining more of this type of query. On 14.2. Now when we go to number 12, so then what was your approach on number 12? Or did you get a chance, number 11, or did you get a chance to get to it? Because after all, you guys were doing a test. So it's understandable some of this didn't get done. But Stuart finished his test Thursday, so he did number 11 on Saturday. So that means Stuart's going to come up and show us how to do number 11.
Yeah, on the board?
Hey, of course you are.
Oh, gosh.
I did a weird thing with my homework. I did the quick checks for the 14.2, and for the questions assigned for 14.2, I was doing on 14.3.
I need my chair. Oh, you can use my chair. I'll use another chair.
So
Well, then that leaves you
I only
in a
had
good position to benefit from what
the
Stuart did.
first quick checks.
Okay. So first of all, everybody look at the picture. Okay, you got the picture? It's got this little cup there, slanted sides.
Which one are they?
Put a page, for antiquity, let's do it in the upper right-hand corner, right, section 14.2, page 1015, number 11.
So it's three shapes.
Sir, I have a question.
Yes.
Oh, no, it's close, yeah, I see, it didn't look like a drawing in the book, I see what you're doing. Okay.
It's that and that. And the difference, which I learned on Saturday, is that these are all three different lines. They all have their own y equals mx plus b. Or mx plus b. So instead of like a single curve, all three of them are different, so you have to do all three of them separately. So for this shape, basically y is static at the top and bottom, so it's between 3 and 1. So for all three of them, you can integrate up top between 3 and 1 for y, but the x part is what varies between the left and the right. What are the equations? So
Well, and is it really 2 and 1? Because it starts on 1, but it goes to 3, so it only really increases by 2?
Yeah, that's right.
right, so it starts at a 1 down here and goes up to 3.
Okay.
And then, so, slope. So for the first one, 3 minus 1 over 1 minus 2.
That's y2 minus y1 over x2 minus x1.
For
So
the,
it's getting the slope of the slanted sides.
for part A. And then B, those equations are simpler, they're just straight lines, so the slope is 0.
Mm-hmm.
And then the other side is 3 minus 1 over 5 minus 4. So the slope for A is negative 2, and the slope for B equals 2. So, and y equals y minus y1. Do all those equations. Does it give you the? No, I'm gonna actually have to solve it on camera.
Commercial page. Good job. So he's finding B. He's finding the missing number in the two equations. Okay.
So the equation for this line right here is minus 2x plus 4. So when you integrate for y, you do the left boundary and then the right boundary, so lowest to highest. So the bottom boundary is negative 2x plus 4. And then this point right here.
Draw vertical slips. Draw vertical strips. Yeah, it's a vertical strip. And the top limit is 3.
2. So this is the point 2. So it goes from this line over here
Okay, yeah,
to
to the top.
oh,
You have to do the y integral first. If you do the x integral first, then you have to solve the equation for x. So you have to match them correctly.
so it's y equals 3.
Y equals 3 is the top.
All right.
Okay, so we see how that's done? He's integrating out y.
So I'm going from this line here to negative 2x plus 4 up to y equals 3.
That's key right there, you see that? Okay, good.
And then the other side,
Well, no, you have to do the x limits on that piece.
oh,
What are the x limits?
so x goes from
1 to 2.
1 to 2. 1 to 2.
Good.
Is that what
Okay.
you said earlier?
Mm-hmm.
Yes.
And now the box is not challenging, and the one on the right is done exactly the same way. So you do 3 pieces. Yeah. Trouble?
So for the one on the right, it's the lower y value up to the top y value. So the lower y value,
It's the same.
It's a different line.
this line has that slope, but I think the points are the same.
Oh,
Well, the B value is going to be different too. You have to.
So
it's 2.
we can pretend.
Okay.
So the upper value for that would be also 3.
Mhm.
Yeah.
So
Good, you're catching
we'd
on.
be integrating from that up to that for y.
AJ, you follow okay? Not too well. It's a hard topic.
Now, I thought though, because I was checking myself with the back of the book, and it's 2x plus 5 is your first equation.
Well, he's not responsible for
Oh.
arithmetic. He's not responsible for arithmetic.
Is that where it is?
No,
Yes.
Is it the 2?
no, it's not an
Yeah.
arithmetic course. It's a calculus
Oh,
course.
that's fine. I just wanted to make sure.
Yes. My arithmetic is awesome.
Okay. Now, what he did is part A, 11A. Catch it? And the box has 3 pieces.
Yes.
Now, 11B is simpler. If you do the x integral first, then you only have to do 1 piece. So now he gets to draw his horizontal lines. So can you change to a blue marker? And now draw a horizontal strip all the way from the left to the right. Now this horizontal strip is going to go from the inverted x equation on the left. Now, can you invert that equation on the left? Y equals 2x plus 4, solve for x. Plus 5, as we've been told. Now, solve for x. Okay, good. Now, you also get an x equation on the other side, don't you? It'll be something. So now your integral over dx just goes from that curve, lower curve, to that other curve.
You have to change that on camera. It's not gonna look right.
Okay. Hi. Okay. So now this is a one-piece integral, agreed? So after you get the blue strip,
What's that?
then what are the limits on your y integral now? After you get the blue strip,
1 and 3.
no, from 1 to 3, yes, from 1 to 3. Y integrals from 1 to 3. So these blue strips are easier than the red strips, agreed? Because you can just do it in 1 piece. You don't need 3 pieces. Because the termination points don't change over the region of integration. But when you did the vertical strips, then the lower limits changed. So you need 3 pieces. Good? Very good. So now it's dx, dy. dx comes first now. Good. And some function of x, y that doesn't matter. Okay? So that's how you interchange these limits, or how you take your choice of limits. You can do either one you want. But you use the equations for the lines. You have to invert them when you invert the limits. You invert the equations. Okay? That's all we can teach. The rest is just doing and studying. Study the examples, work them, and go to step 2. So well done, Stuart, and we're at this point now. So now I have to ask, are there any that anybody is prepared to put on the whiteboards from these 2? Now, when we go to the next section, we do exactly the same stuff, only we do it with r and theta. But nothing fundamentally changes. It's still a volume integral that's using 2 variables, and you can either have fixed limits, which is very easy, or you can have simplistic varying limits. So Stuart has a leg up because he had the weekend to work on it. But this is hardcore calculus. It's nitty-bitty in the middle, it's intricate, it's hard, and it's the way calculus is done. So we're not going to skip over it. We're just going to dig in, and one way or another, learn to do it. Because if you learn to do this, then you're doing calculus. there are other things that are so easy, you're not really sweating. So this one is giving you a taste of it, the real stuff. So we're not going to skip over this, but let's go back to my query. Are there any of these assigned problems, including the quick checks, that people are prepared to whiteboard? So we're sections 14.2, 14.3. Do we have any at all?
I have most of them.
You have most of them. And AJ?
Back to check one.
On which one, 14.2 or 14.3?
Well,
Both?
no, I did this rating one in a mix 14, 2, and 3.
Okay, so you have some quick check. One of them. Lynn, what can you contribute? Monica?
I did all the easy ones. So I did 1 through like 13 maybe on the first one, maybe 1 through 16, and then on 14.3 I did 1 through 6.
Well, that's admirable. That's quite a bit, actually.
I just did the stuff that I knew the limits on. Anything else I couldn't figure it out.
I understand. Well, Stuart is our honcho on that. He can fill us in.
I don't know if it was a sign on 14.3, but I got 1, 3, and 6 on 14.3.
1, 3, and 6. Similar. Okay, just so we get something on the board. On 14.3, AJ, why don't you do 1, 3, and 6? And Monica, what other ones on 14.3 did you say you had, 2 and 5?
On 14.3,
Yes.
I have 1 through 6.
Okay, can you do 2 and 5?
Okay.
Okay, now, any quick checks, Stuart, we'll give you some in a moment, but any quick checks that you want to volunteer for, AJ?
Which one?
Either one.
I got 14.2, quick check 1. That's about it.
Okay, 14.2, quick check 1 is AJ's. Monica, any quick check you want to volunteer for?
I can do 2, I think,
On which one?
on the one we're working on, the
Um,
14.3, right?
14.3, okay, that's a whole according. Okay, now, Stuart,
Do the rest.
why don't you choose 3 problems of your own choosing, where we have to do these things that these guys need some trailblazing for, like interchanging the order of integration or integrating between curves. So why don't you choose 3 for yourself from both sections, 14.2 and 14.3.
Or the ones where they change it.
Okay, well, while you're pondering, let's pull the whiteboards out and start throwing stuff up. That's going to block the camera, so put it way deep, deep. Yeah, that's good. Thank you. So, Monica, I'm real pleased that you did that for your missed class. You didn't just sit, you got it done.
Well, I didn't get it done, but
Now you got 50% of it done. You can't be expected to do this kind of stuff without presentation. It's interesting. Thank you, ma'am.
What event? We're doing it about doing quick checking.
That is a fundamental. This is nicely presented. You see the file. Appreciate it. Now I'm going to go down to my mailbox and fetch one more. I think I'll check out the testing room too.
I really don't like polar coordinate volumes.
they were
I
hard.
didn't like